whenever you see the molecular formula, the first thing, probably nice things to do is to calculate the degree of unsaturations. So that would be the number of the carbon, subtract by the half of the hydrogen, subtracting by the half of the halogen, adding half of the nitrogens, plus 1. Don't forget the plus 1 in the end. Oxygen does not contribute anything for the degree of unsaturations. Anyway, if you do that, 3 minus, and then I put those two together because there's a 5 hydrogen and then 1 bromine. So if you put it together, that would be kind of cancel it out. So we got only 1 degree of unsaturations. So 1 degree of unsaturations. That could be double bond, or that could be cyclic structures. I don't know. Well, our spectrum is here. One thing that you can see immediately is, can you see what it has? It has a carboxylic acid, right? Carboxylic acid has a very broad signal centered at 3000. This very broad signal centered at 3000. That's a carboxylic acid. So we do have a carboxylic acid. That's what I can say. And then this carbonyl is definitely coming from that, so it's not really new. And then, nothing else we can get it out from the IR. At least the IRs are pretty limited in a way, but it gives out this, presence of some functional groups. Moving on to the mass spec side, what is striking is this one. Now you see it because we just talked about this issue before. You got 2 peaks, like 2 masses apart, equal height, means we have a bromine. So that is something that tells us we have a bromine. And then there's 152 minus bromine, that's this one. So you can do the math and you can figure out that's the one without the bromine. And that's the reason why it doesn't have a satellite peak, n plus 2 equal height. Well, but other than that, nothing really we can get easily. So that's what I'm going to get. And then let's move on. What can we see here? We give an integration here, 2 hydrogen, right? So we give, so what else is kind of showing up? We got 2 hydrogen here. That must be CH2. There's 2 hydrogen must be CH2. I don't know whether they're going to be connected together or not, but there's a possibility there. This is kind of hard to see, so that's why I'm kind of putting it out. That's a triplet. So, oops. So that's why this is a triplet here that caused by this. That triplet is going to be caused by that. And then this is a pretty small molecule. We're sort of only 3 carbon, 5 hydrogen, 1 bromine, 2 oxygen. So let's find out we got everything. So 1, 2, 3 carbon, 5 hydrogen, 1, 2, 3, 4, 5. We got all the hydrogen, 1 bromine from there, and 2 oxygen from this. So there's no other pieces that we need to find. We got all the pieces found. Then we need to put it together. So this is kind of open-ended. This has to be connected. That's connecting there. This is connected to bromine. So that will give a structure like this. We didn't use the carbon-13 at all. Sometimes you don't have to use everything, but we can use it, double check. There's a carbonyl carbon, yes, giving a signal here. And then that's a solvent. That's what I told you about. If the NMR was taken deuterated chloroform, you're going to see the carbon signal of the solvent in the carbon-13 NMR. So that's a solvent. And then those two is kind of an aliphatic range. Those 2 carbons showing signal, very upfield because it does not having an oxygen there. Having a bromine does not pull it down too far either. The oxygen does it very strongly, but not others. So this is a pretty simple question. I'm pretty sure that this is kind of a warming up right now. Next one. Now we got 8 carbons, and then 14 hydrogen, and then 4 oxygen. I like this question. I'm really sorry to spoiling this question to you. So in case you want to solve it by yourself, cover your ears, because I'm gonna give you spoilers. But anyway, all right. What can you find out here? Starting from the IR, what can you find here? We got the big, strong band at 1750. That means we have degree of saturation first. 8 of the carbon minus 14 divided by half, and then plus 1, that will be 2. We got 2 degree of saturations, okay? And then there's a signal 1750, which is a pretty, the higher frequency compared to the regular carbonyl, which is 1710. So I can say that this must be aster. This has to be aster. So we have an aster. Okay, that's what IR telling us. All right, if you look at that, the carbon-13, we got the 178 signal right here, too. So that's good. So it's kind of a cross-confirmed, which something that sometimes you need to have that. It only appears here, but you don't have this signal, then it cannot be the aster, right? So sometimes you really have to look for the surprises by checking things out thoroughly. What I'm telling you is, how many carbon-13 signal do you see here? 1, this is solvent, 2, 3, 4, 5. We got 8 carbons, but it only gave out 5 signals. So what does it mean? 5 peaks for the 8 carbon means it has a symmetry. That's something that you should find out. That's the carbon-13 could be useful. If there's all different, you got 8 peaks for the 8 carbon, that means every carbon is different, there's no symmetry at all. If the numbers are lower than the number of the carbon, some part, not every entirely, some part must be symmetry there. Here's the thing. Carbonyl is going to show up. We got symmetry. I mean, this is kind of a point out that this is CO2, right? Ester is a C1 and O2. We got 4 oxygens. I mean, of course, there will be 2 ethers somewhere around, but it could be possible that it may be 2 ester, right? If there's 2 esters, no symmetry, we should have seen the 2 signal here. But we only see the 1 signal. So that means the molecule might be entirely symmetrical. So 2 ester might be definitely symmetrical. That's why we only see 1. I mean, there are probably other things that you need to find out. There's a carbon here too, right? This has to be connected to the carbon. So the carbon bearing on oxygen will show up. But you can see there's only 1 carbon bearing oxygen. Even though we got 4 oxygen. I mean, there's 1 carbonyl, but somehow 2 ethers, then that will also make 4 oxygens. But if you look at that, just 1 carbon for the bearing oxygen. So that does not make any sense. So this means that we really have to have a 2 ester. And then that 2 ester is symmetrical. So that's kind of what we can gather from this. So what that means is, and there's another thing. Ester part, this has carbon must be attached there, and that carbon bearing a hydrogen should show here, because that's the one pretty downfield. And then you see this is kind of a hard to splitting, but I said there's a quartet, that's triplet. You get a quartet triplet combination, 2-to-3 ratio, and that is ethyl, right? Ethoxy, most likely, because of the chemical shift down here. But you got the 4 hydrogen and 6 hydrogen. I mean, 6 hydrogen, maybe 2 methyl kind of being the same and showing together, but the 4 hydrogen being together, that's kind of hard to imagine by the 1 carbon. It must be 2CH2 and then 2CH3. I mean, the 2 ethyl groups are in equivalent positions. So that's kind of things I can say. 4 hydrogen, 6 hydrogen is a double of the ethyl groups. And then the ethyl must be symmetrical too. That's why it only gives 1 signal. So combining all these things, I can say this. There will be a ethoxy group, definitely, right? CH2, CH3 having an oxygen is pointed out by this chemical shift. And then we'll have another methoxy group, and it will be symmetrical. That's why you can have only these patterns of signal, but double the amount of hydrogens. And then we know this is an ester, so I can say that must be the carbonyl there, right? So at least I can gather that. Once you find out this much, then I guess we'd like to find out what's missing, right? So what I would do, I kind of figuring out, what's missing. It's an 8 carbon, 14 hydrogen, 4 oxygens. I found a 6 carbon, 1, 2, 3, 4, 5, 6, and a 10 hydrogen, 5 here, 5 there, 10 hydrogen, 4 oxygens. If you subtract that, we got a C2H4. So how many ways can you have a C2H4? One way is of 2CH2 put together. That's the one way. But the thing is, you got 1 hydrogen here, 3 hydrogen there, and that's a doublet, that's a quartet. So if you have that, suggested by this, it wouldn't make sense because it wouldn't give these splitting patterns, and then integration is definitely different. 1 hydrogen and then 3 hydrogen, quartet, doublet is not caused by this. So we can exclude that out. What would be the way to give a quartet 1 hydrogen triplet, the doublet in the 3 hydrogen? That would be CH connecting with the CH3. That's the only way you get that. And then this is C2H4. So we finally found every piece is together. So where that piece has to go? In the center. That's the only way. So you put it together like this, then you can see that this molecule simplified down. That methyl groups is this one, right? The doublet here. And then that CH of that is a quartet, but it's such a D-shielded because it's next to the 2 carbonyl. By having a 1 carbonyl, it'll be pulled down to maybe 2.5. By the 1 carbonyl is 2.1 or 2, but having an oxygen there is going to pull a little bit further away. I may say maybe 2.5 and 2.6, but having another set of the esters is going to pull down further. I'm expecting between 3 and 3.5, and then it's kind of showing that where it's supposed to show, right? A little bit over the 3. So I know it's kind of estimating, but you got you can change a little bit, but at least it's in the right range. And then 2 ethyl groups are equal because of symmetry of the molecule, which it shows right there, 4 hydrogen, 6 hydrogen, behaving as a group. So everything makes sense. So once you figure that out, and then we can say that must be the answer. So you see that the symmetry, it can make things difficult for you. You got to recognize it. And one of the ways to recognize there's a molecular symmetry is that sometimes you can look at that as a proton NMR, like a 4 hydrogen, 6 hydrogen, kind of being the same group. There's nowhere other than symmetry in there. Or the carbon number of the carbon signal, right? Less than the number of the carbon in the molecule. So this is kind of a way to find out if the molecule has symmetry. Any question on this? I guess I'm being so clear today. Or you don't get it at all, right? Well, go over again. I'm going to post this video, so you hopefully second time or third time, maybe something clicks. All right, next one. C8H6O2. So first thing to do, degree of unsaturation, 8 carbon, divide by 6 of the, why did I say 3? It must be 2, sorry. 2. I prepared this thing right before I come to class. I kind of rushing it out. So it must be 2. So that, and then plus 1, and then, so that must be 3 and 5 plus 1. That must be 6, yeah. I did the right, and I just didn't write it correctly. So 6 degree of saturation. This is pretty high degree of saturation. But if there's a benzene involved somehow, that can account for. So we'll see. What else we do see here? There's a strong band. What's the number? 1693. 1693, not 1710. It's a little lower. Carbonyl, but conjugated carbonyl. Could be conjugate to the double bond, conjugate to the aromatic ring like a benzene. So it must have a conjugated carbonyl there. So that's what this can say. What else can you get from this IR spectrum? You have to find something really critical one from there. Of course, you can find somewhere else. Yep. You have a 2700, 2800. It's kind of a small. It's really not standing out as a carbonyl, but it's there. Otherwise, you wouldn't see those two. So we have an aldehyde. But having an aldehyde can be confirmed other way because this hydrogen will show right here, proton NMR, right? Proton NMR, something between 9 and 10 must be the aldehyde signal, and that must be it. So, and then there's carbonyl of the carbon 13 NMR. That is a carbonyl here, but it's pretty small. You have to squint your eye to see it. There's a D means, right? D means that's doublet. When we allow the splitting happen, that peak could be a doublet. Doublet means this carbon should have a one hydrogen, and that's an aldehyde. So we can confirm presence of aldehyde in a multiple way. Sure, this is a one way, but that also can confirm too. And this is a little bit over 10, but you know, this thing can move around a little bit. So I think that's still within the range of the aldehyde. So we have an aldehyde there. Great. What else can you tell from the carbon 13 NMR? We have 3 peaks for the 8 carbons. It's a really small number of the peak. I mean, previously, when we have an entire symmetry, C2 symmetry, I don't know, you probably don't know these things, right? Never took it the group theory, right? All right, it's a mathematics, but the chemistry use it. It's kind of telling us the symmetry in the molecule. There's different types of symmetry. Like if you can turn the molecule 180 degree or the 60 degree, then you make everything same. And then or sometimes you get the planar symmetry. You know, this is kind of a thing. It's a remarkable mathematics. I enjoy it, of course, but I don't have no use for that afterwards. But that's kind of what it is. We got with the pretty, C2 symmetry there. But this one, I don't know, 3 peaks for the 8 carbons, a lot smaller number of the carbon peak. So you should look for the symmetry significantly here. What else we do see here is, definitely aldehyde, each hydrogen should show up, but we got 2 hydrogens at the same position. So that means the 2 aldehyde must be really symmetrical. Otherwise, you get the 1 peak and then account for the 2 hydrogen. So must be the aldehyde at very symmetrical positions. So I put the 2 down there. All right, and then I know this is kind of a maybe a little too early you say, but sometimes you do this multiple times. I know there's 2 carbons, 2 oxygen, 2 hydrogen that's coming for the 2 aldehyde signal. If you subtract that, you get a 6 carbon and 4 hydrogen left. And then there's an aromatic hydrogen here, a carbon here, right, between the 100 and 140. So this must be the aromatic region. It could be double bond too, but it could be aromatic regions. So, but you see only 2 carbon for the benzene. So benzene must have a highly symmetrical. Otherwise, you would have that. So 6 carbon and the 4 hydrogen, and that must be the aromatic one, benzene like this. And then we got the peaks at the 8, that's the aromatic carbon hydrogen range, and 6 hydrogen there. So clearly, that's 4 hydrogen. 4 hydrogen of the benzene must be there. So how can you put the 4 hydrogen in the benzene? There may be multiple ways. 4 in a row, that's the one way. Or you can put 3 and then 1 opposite side. That could be ortho substituted, meta substituted, or you get the 2 here, 2 down there, the para substituted. Which of these do you think is what we need here? And how can we tell? It could be any, right? But answers are very much in this place. I want you to see that this is a singlet. You got singlet for the 4 hydrogen of the benzene. What does it mean? If this is this pattern, I mean, one, you think that should be doublet made by this, that should be doublet made by that. So you are excluding that possibility out, probably, right? Anyway, there will be a lot more complicating splitting. This splitting, that splitting, this is splitting. This is a really high, that makes you have a lot more number of hydrogen. And then this one too, there's a probably, that may be singlet, but you got splitting happen among those three. So these two would be really bad. But if you got the pair substituted, but symmetric also there too, then all the 4 hydrogen becomes unequal. Then it'll be singlet. And then I told you these molecules are highly symmetrical. So that's kind of what makes sense. So even this small thing, yeah, that 4 hydrogen here, this picks a singlet, that is actually telling us what's the pattern, what's the position of the hydrogen in the benzene ring. So NMR is really powerful. It tells you something. Sometimes you see it, but you don't get it. That's kind of a problem. But only the trained eye can see this thing. Anyway, so that's why I said not this possibility, not that possibility. Only way to have a singlet for the 4 hydrogen, and then 2 carbon in the carbon 13 signal is this way. That's the only way. You get this carbon is the same as that carbon. All those 4 carbon in the middle becomes the same. That's the reason why you get only 2 carbon 13 signals of the benzene in the carbon 13 NMR. All right. Is that all we have to find out? Yeah, I guess we found every pieces. So now we need to put it together. So 2 aldehyde, and then we have this para-substituted benzene, and we just have to connect it together. So that's the molecule. It's very symmetrical, and that's the reason why the spectra is kind of simplified.